A motorcycle stunt rider moving horizontally takes off from a point 1.25 meter above the ground, landing 10 meters away as shown. What was the speed at takeoff? So the speed, the motorcyclist leaves this point here a little bit above the ground, is the horizontal speed. Because the trajectory of this motion is look like a horizontal launch, so we are going to study this problem as setting up two tables. One is a horizontal table and another one with a vertical table that shows that the velocity, the vertical velocity, is going to accelerate downward, start from 0 and accelerates downward with the acceleration of gravity. Here I'm showing all my work, but I'm going to explain from the beginning. So this is a typical type of horizontal launch motion. So in this case, we have two components of the velocity. One is horizontal, that remains the same the entire time. And the other one is vertical, we can view as a free fall. So for horizontal, the initial velocity and the final velocity remains the same the entire time. And the distance here is the horizontal distance. It's like that you are scanning the problem horizontally. So everything you need to see in this direction. So the distance here is 10 meters. Because the velocity is not changing through this trajectory, the acceleration is 0. And the time they stay in the air up to hit the ground, we are gonna call horizontal time. Like I said, vertically, we are going to see this motion as a free fall. So the initial velocity here at this point is 0, but is going to gain velocity over time because it's at the same direction of the acceleration of gravity. So the final velocity vertically, we don't know, is going to hit the ground with a final velocity, which is this one, VF. The vertical distance is 1.25, which is this, like we just did horizontally. Vertically, we're going to scan everything is in this direction. The acceleration of gravity downwards is accelerating, so it's positive 9.80 meters per second square. And the time that it stays in the air, we are gonna call TV. Now, for the horizontal side, since the acceleration is 0, we are using the fourth equation of the list that I gave you. So VH is DH over TH. Notice that I'm using here H to mark that is horizontal motion that we are looking at. So we have the H, which is 10, but we don't know TH, but we can calculate TH using the vertical data table. So in this vertical data table, the formula that gives us the time, the vertical time, is the second equation simplified because the initial velocity is 0. So, and because the acceleration is 9.8, half of 9.8 is 4.9. So this is why we have this equation right here. So since we are calculating the time, so our time here vertically is 0.5 seconds. Because the vertical time and the horizontal time have the same value, so the horizontal time here is 0.5, and calculating this VH, 10 divided by 0.5 is 19.8, which is approximately 20, so answer D is the correct answer. Second question, a boy throws a ball vertically upwards. It rises to a maximum height where it is momentarily at rest and then falls back to his hands. Which row gives the acceleration of the ball at various stages in its motion? Take vertically upwards as positive and ignore air resistance. So here is the diagram to describe this question. So the ball leaves the hand of the boy, goes up, and comes back to his hand. If we ignore the air resistance, so the only acceleration that is acting on this ball is the acceleration of gravity, G. Now the problem also states that take as a reference a vertical upward as positive. However, acceleration is acting downward. According to the problem, is acting in the negative direction. At any stage of this motion, when the ball is still at rest on the boy's hand, going up, stop in the middle of the air, and comes down back to his hand, at any time, the acceleration on the ball is the same. G is equal to 9.8 meters per second square. It's the same the entire time. But because the problem says take vertically upwards as positive and the gravity is downward, so we are going to select option B that shows that any stage of this motion as the ball is rising at the maximum height when it stops right here, and when it's falling, all negative 9.81 meters per second square. Question number 3. A projectile is fired from point P with velocity V and angle theta to the horizontal. It lands at point Q, a horizontal distance R from P after time T. The acceleration of free fall is G, air resistance is negligible. Which equation is correct? So I'm going to analyze this problem the same way that we do with projectile. But in this case, we don't have any numerical value. Everything is in letters. So let's see what we get. So first, the component of this initial velocity here is our VH, and this is our VV. So this is a good way to start, to find the components of this initial velocity in terms of this angle. Okay, so VH is adjacent to this data, so I'm going to use cosine. So cosine of this angle is VH over V. And if I move this vector right here, so now I have my VV, right? So I don't duplicate, I just move. So I cover this one so you can see better. So the opposite here is VV. So I'm gonna use a sine because sine of this angle is the opposite over hypotenuse, which is V. Then my VH is V cosine of theta, and my VV is V sine of theta. Now all the options is showing R. R is our horizontal distance. So we know that horizontally, the velocity remains the same at any point through this trajectory. So we can say that DH is equal VH times TH. So the horizontal distance is the horizontal velocity times the total time in the air. So my DH here is represented by the letter R. And the VH is V cosine of theta. And my TH should be the letter T. Why? Because it's saying from point P to point Q, the entire time is T. So here I'm going to write just the letter T. Now I'm going to rearrange V and T. So R is VT cosine of theta. And I have a winner right here, which is the option A. Question 4. In the absence of air resistance, a stone is thrown from P and follows a parabolic path in which the highest point reached is T. The stone reaches point Q just before landing. The vertical component of acceleration of the stone is a couple of points here that we need to identify in this problem is this, the absence of air resistance. So in the absence of air resistance, gravity is the one acting the entire time. So gravity, the acceleration of gravity throughout this trajectory remains the same. To answer this question, the vertical component of acceleration of the stone is 0 at T. No, acceleration is acting here. Greatest at T. No, acceleration is constant. Greatest at Q, acceleration is constant. The same at Q as at T. Yes, because acceleration is constant, remains the same at any point of this trajectory. So the answer is D. Last question from this page. An insect jumps with an initial velocity of 1 meters per second, reaching a maximum height of 3.5 times 10 to the minus 2 meter. Assume the deceleration is uniform, which means there is no change in the deceleration is constant. That's what I mean. Uniform means constant. Whatever is happening at the same ratio, same rate. What is the magnitude of the deceleration? So here is a diagram show the insect jumping with initial velocity reaches the maximum height where the final velocity is 0, and the height the insect jumped is correspond to 3.5 times 10 to the minus 2 meter. So based on the story, I set up this table. VI is 1 meters per second, VF is 0. That's the maximum height. Other time they say maximum height. That means that the velocity right there is 0. And this one to calculate the acceleration, and time was not provided. So based on the equations 1, 2, 3, and 4 from your foldable, so VF squared is equal VI squared plus 2AD. Time was not provided, so that's the perfect equation for this. So final velocity is 0, initial velocity is 1 times 2A, and that's the distance. So the problem is going, not the problem, but the way that the equation is going to lead you to a negative acceleration, which makes sense because the is decelerating. It starts from 1 and at 0. So it's decelerating, that's why the value is negative. There is no negative here on these options because it's only showing the magnitude of the acceleration, which is 14 meters per second squared. Question number 6. A stone is dropped from the top of a tower of height 40 meters. The stone falls from rest and air resistance is negligible. What time is taken for the stone to fall the last 10 meters to the ground? So this is the diagram that represents the beginning of the story. So the stone is dropped from rest So initial velocity here is 0. From a tower that is 40-meter high. Now, your first attempt should be like, okay, so from here to here is 40, from here to here is 10. So I will say that when is like 30 meters, you need to be careful with this question, because you could say, okay, so why not just use this information right here, right? So the velocity of the stone here, that's the distance, and what time takes for these to fall. You could do that if you know the velocity of the stone right here. So you need to do some calculation to figure out the velocity. So when you have this velocity, and then you can easily calculate the time. There are two ways to solve this problem. I'm gonna show you the first one. So this is the data table. If I'm going to look just where the ball is to the ground. So to do that, I need to know what is the velocity right here after left this tower. So I know this is 40 and this is 10. So here is, this distance is 30 meters. So I want to know the velocity of the ball right here. So then I set up this data table. Initial velocity is 0 when left the tower. The final velocity, this is what I'm looking for now. The distance is at 30 meters after left the building. The acceleration is 9.8 meters per second square. And I don't know this time. So based on the 4 equations, the one that we don't have time, so I select this third one. VF squared is equal to VI squared plus 2AD. So VI here is 0, so I just have this left. 2 times 9.8 times 30, square root of this is 24.24 meters per second. Great. Now that I know the velocity here, which is 24.25 meters per second, then I can look this motion independently, what happened before. So I have this velocity right here. I have the distance, which is 10, and I'm looking for the time. Okay, so now I'm going to set up my second table. So my second table is right here, based on up to 10 meters off the ground. So the initial velocity right there is 24.24, which is a calculate here. The final velocity is irrelevant. I don't know the velocity that is going to hit the ground. I will have to calculate. Acceleration is the same, and this is the time. So based on the information on this data table, let's see if I can solve using the second equation. Looks like I have everything. I have distance, which is 10. I have the initial velocity, and I'm looking for the time. The problem is, to solve this equation, now I have a quadratic function that I need to calculate. It's gonna be too much math here, so I don't want this. So let me try the first equation, because what I want to find is time. So the first equation, I have time, but I don't have this final velocity. I do have the initial, but I don't have the final. Okay, so how to calculate the final velocity? So then use the second equation, because you don't need time. So, and then we have the distance here is 10. The acceleration is the same, 9.8. Initial velocity is 24.24 square, and this is square as well. So then I calculate the final velocity, which is 27.99 meters per second. Great. Now I can go back to this equation here that I didn't want to use because I didn't know the final velocity. Now I do have the final velocity, so I can use this equation. I use this equation, and I calculate the time for the last 10 meters. and that's one of the options, and this is correct. Now I'm going to show you a second way to answer this question. The second way is that I'm going to calculate 2 times. One, when the ball hit the ground from where it was dropped to the ground, 40 meters. And the other time when was left from the tower up to 30 meters. So, and then I'm using just one equation, which is the equation number 2, simplify, because I don't have initial velocity. So d is equal half at squared. So my time here is 2.86. And then I calculate my time. I do the same thing, but now with my distance at 30 meters. So from here to 30. So the initial velocity is also 0. So and then I can use the same equation, simplify. Now my distance is 30. Half of acceleration is always going to be 4.9 t squared. Now this time is 2.47. Now what I'm going to do is I'm going to subtract both times. So when I subtract both times, I get 0.39, approximately 3839, which is one of the options right here. So there are 2 ways to solve this problem. Please do the way makes more sense to you. Question number 7. An object falls 10 meters from rest before entering some water. Assuming negligible air resistance, what is the time taken to reach the water and the speed with which the object reaches the water? Here is a data table according to this story. So the initial velocity is 0 because it says that fall from rest. The final velocity, I don't know. The distance is the height, in this case is 10 meters. And the acceleration is 9.8 meters per second squared. Why? Because it says that the air resistance is negligible. Because if we have to use air resistance, then there is other factors involved that is going to, the acceleration of the object is not going to be this, it's going to be something different. So that's why in this case, because it's negligible, so acceleration is 9.8. And time, we don't know. So this is the data table based on the story. So now is asking the time that reached the water, hit the water, and the speed that hit the water. So we need to find this, and we need to find this. So let's start with finding the velocity, because I can use the equation 3 actually. Vf squared is equal vi squared plus 2ad. So the final velocity, one that I'm looking for, initial velocity is 0. So it's square root of 2ad. So 2 times 9.8 times 10. The final velocity is 14. Okay, that's the final velocity. And I have some options on the multiple choice A, B, C, D that I see 14. But it's going to determine, the time is going to determine each option is correct. To find the time, let's go right here. So the time that takes to hit the water, we can use equation number 2, simplify, because the initial velocity is 0. So d is 4.9 t squared. The distance or the height is 10. So then we can find the time, which is 1.43. So that's the answer is option D. Question 8. Following is the velocity time curve. So this is a graph and is showing the variation of the velocity over time. What is the distance traveled between time 0 and 4 seconds? Every time you see a problem like this, where a graph velocity time is provided and is asking for the distance traveled. So you are going to determine the area under the line graph. Every time you need to determine the distance or displacement of a velocity time graph, we need to determine the area under the line. The area under the line corresponds to a trapezoid. So the formula for the area of a trapezoid is the longer base, in this case this one. If you look at the trapezoid this way, so you have a base and you call also base here. So big base plus small base times the height divided by 2. So that is the formula right here. Now we need to figure out the value of the big base, small base, the height. So then you have to look at this trapezoid. So the big base is this, corresponds to 12. The smaller base is this, corresponds to 2. The height is this, corresponds to 4. All these divided by 2, we have an area of 28 meters. So the answer is option D. So again, the distance traveled in a velocity time graph with uniform acceleration. It's important you understand this. The uniform acceleration, how do we know? Because this is a straight line. If it's a curve, we cannot do this. Not for curves, just for lines. Okay, so the uniform acceleration is equal to the area under the graph. Question number 9. Which feature of a graph allows acceleration to be determined? The area under a displacement time graph. No. When we have a displacement time graph, we don't do area under the line. The area under a velocity time graph. Okay, the velocity time graph provides if it is linear, like in the prior problem, like this, so we can calculate the area under the graph, but will not give the acceleration. You can determine the distance or displacement. Displacement. We have a problem that we solve in classroom that we can differentiate both. Okay, now the slope of a displacement time graph. No, the slope of a displacement time graph will provide information about the velocity of the object in motion. The slope of a velocity time graph, yes. So the slope of a velocity time graph will provide the acceleration. Now in this case, the slope here of this velocity time graph is constant. So any point here that you try to find the slope, rise over run, at any point you are going to obtain the same numerical value. So that indicates the acceleration here is uniform or constant. So the slope of a velocity time graph, if it's a curve or is a line, always going to determine the acceleration. Question number 10. A motorist traveling at 10 meters per second can bring his car to rest in a braking distance of 10 meters. In what distance could he bring the car to rest from a speed of 30 meters per second using the same force? When you see same force means the same acceleration. So what the part 1 and part 2 of these problems have in common? The same acceleration. So on part 1, it says that it's going with this velocity and can bring his car to a stop after 10 meters. On part 2, now he's using a greater velocity and using the same acceleration from part 1, what will be the distance that he's going to stop his car. So this diagram represents the story. So a car is traveling at 10 meters per second, decelerates, and comes to a stop after 10 meters. So now the car is at 30 meters per second with the same deceleration, is going to stop at what distance? First job, to find the value of the deceleration that will produce the car to stop. So, because time here was not provided, we are using the third equation, I'm sorry. Vf squared is equal Vi squared plus 2AD. The final velocity is 0, the initial is 10, the distance is 10. So this way we can calculate the acceleration. Okay, actually this is the value of deceleration. So now we are going to the second part of this problem. So here is the data table for the first part. Initial velocity is 10. The second part, the initial velocity is 30. The first part of the problem, the car go to a rest or stopped. So the final velocity is 0. Likewise, the distance, the time that the motorist press the brakes to a stop is gonna be 10 meters. I want to know how much will be this distance. It will be less, it will be greater. And the acceleration here, we calculate, which is the negative 5 meters per second squared. That is not showing here, but that's the deceleration. And now the same deceleration will be applied for the second part of this problem. Time was not mentioned, so now I'm gonna use this information to calculate the distance that takes for this car to go to a stop. Will be greater, will be 90 meters right here, 90 meters. That's the final answer. Question 11. A car is traveling with uniform acceleration along a straight road. The road has marker posts every 100 meters. When the car passes one post, it has a speed of 10 meters per second. And when it passes the next one, its speed is 20 meters per second. What is the car acceleration? Here I'm showing all my work, but I'm going to explain all the steps. So this diagram here represents the story. So start with 0. So every 100 meter, there is a mark. Another 100 meter, another mark, and so on. But the problem says that as the car passes through the first mark, which is after 100 meters, its velocity is 10 meters per second. Then go to the second mark, 100 meters later, you'll be 20 meters per second. So how we are going to create a data table for that? The initial velocity here in this interval is 10 meters per second. The final velocity here is 20 meters per second. The distance between both posts is 100 meters. So that's when students get confused here. They think should be 200 meters. No, it didn't include this section. It's giving information after the first and after the second. So here we are looking this section. So the distance between both is just 100 meters, not 200, 100. So 100 right here, and want to find the acceleration. So the best option for formula is the equation number 3, because time is not involved. So Vf squared is equal Vi squared plus 2AD. I have everything. I have the final square, initial square, 2A, the distance is 100, and this acceleration is 1.5 meters per second square, option B.